Okay. Anybody? Oh, before I get into that, so what do we have coming up? We have the exam. Next Monday. And let's do topics up through, let's just go up through 2D rigid body statics. So today we're going to get into 3D rigid body statics, but the stuff starting today is not going to be on the test. And I will give you a, let's see, what am I going to give you? I'll give you any equations you need, but I'm not going to give you a list of the joints. Okay, the meaning of the joint. So you either, you can, there's two ways to approach those. You can memorize what the individual joints do, or you can think through what they do based on what degrees of freedom are eliminated by the joint. Or probably the best way is to kind of do both, and then you have kind of a check on your thinking from one, So that means like you see a pin joint and you think like, okay, I think that's two forces and no couple. And then you think, does that make sense? Like, yeah, you can't translate along this axis. You can't translate along this axis, but you can rotate. So there have to be two forces to eliminate those translations, two components of force, but no couple to eliminate the rotation. Okay. So I won't give loads applied by each joint. So you need to be able to come up with that yourself. Anyone have any questions about the test? Anyone want to see any homework questions? Yes.
Can we take a look at 7?
Sure. Let's see.
We might be moving away from just doing the free body diagram.
Okay.
Not actually doing anything on that.
Click, 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 click. Takes like 7 clicks to get into D2L. How many clicks to get into the center of D2L?
Gosh, Canvas is worse.
Is it?
I don't like it. It's very nested.
Mm-hmm.
Everything, it's like systems within systems.
Okay, assignments, and then we got rigid body statics. Holy moly. I remember this one. Okay, I'm going to do it, Graham. You better be right about this. If I copy this and it doesn't copy, I'm going to be mad.
Stake my reputation on it.
Okay, better be copied.
Oh, wait, hold on. I have a caveat. Did you do Control Windows S to do that?
No.
Do Control Windows S.
Okay, let me see if what I did is. That worked fine. I didn't really do anything. Okay. I just chose the selection and then it auto-copied, I guess.
My reputation is safe.
Yeah.
Or shape. How would you draw the force for that one?
Yeah. Okay, so actually, let's go through this because I mean, I know this is confusing for lots of people. There's lots of directions, and okay, so start with a free body diagram, and you have this thing at a 45-degree angle. There's a weight force at the center. The mass is 850 kilograms. It's made out of that stuff from Black Panther. 850. Anyone have that weight in front of them?
8,338.5 newtons.
Okay, 8338.5. And then up here, this is a pin joint. So pin joints are forces with an unknown direction. I'll call this R. And then this one makes an angle of 20 degrees with the vertical, and the force is perpendicular to that. I'll call that N. And with pin and slot joints, you don't know which of the two directions that force is going to be. So you could draw that the opposite direction of this. The numbers will all come out the same. So if I'm looking at this and it looks to me like it's going to be in this direction, but if my intuition is wrong about that, I'm going to get a negative answer for N, and that just means it's really going the other direction. Yeah.
Yeah, so this is actually where the question comes in. I had the same thought for N, so cool. Why isn't it just that simple? You've got one force going down, it would push the Y value for the R down, and it would push the N value towards R.
Okay, I guess here's why. It's because this thing can't go anywhere. So because of this joint, all this can do is swing around in a circle around this, right? And so it's trying to swing around in a circle, but at that point in a circle, the a tangent to that circle is at a steeper angle than this, and so this has to fight back against it, I guess. But we're going to very quickly get into problems. Once we start doing collections of rigid bodies, there's just going to be a lot of cases where you just don't have much intuition about what's going on. So that intuition isn't really going to be that crucial a thing. You use intuition a lot of times to sanity check your answers. Like, does this make sense? For me, if I'm doing problems with a whole bunch of bodies connected together, I don't really try to have much intuition about what's going on. I think all you can do if you really need to get a problem right, like in school, in classes, you don't have a lot of cases where you just really need to get a problem right. In research and in jobs, any kind of job, I assume, there are times where you need to get it right, and in school, you don't really emphasize that. If you get it 90% right, then you're happy or whatever, Well, what I usually do is, in cases where I'm depending on getting that answer right, I do the problem, I wait hours or a day or something, I do the problem again. If I get the same things, then I feel good about it. If I don't, then I do it again. That's really all you can. Sometimes you can come up with roundabout ways to check stuff. Try doing calculations different ways, but that's really takes the place of like intuition in the case of really complicated, you know, collections. Okay, so we got this. And I'm going to make my about point here. It doesn't matter where you put it. So first is this R force that's at the about point. So the row vector is 0. The force is Rx, Ry. Cross product is 0. Next, I'm going to do this N force. And I'll tell you in a second why I skipped the weight for now. Okay, so the row vector. This is why, like, I put this on quizzes and stuff. Like, this should always be at the tip of your tongue when you're doing these problems, just to make sure that you're doing that row vector right for calculating the moments. The row vector is the vector from the about point to where the force is applied. Okay, so I'm going to sort of think of that red dot as my origin, and I'm going to calculate the coordinates of where that N is applied. That angle is 45 degrees. The length is 4 meters. And so this is going to be negative. It's going to be 4 times, write it down here, 4 times cosine of 45. And then this is negative because it's in the third quadrant. 4 times the sine of 45 degrees, negative. You could also think of that as, you know, draw out your coordinate system. We want a vector like this. This is 45 degrees. So from the positive x-axis, that's 90, 180, 225. So you could do this as 4 times cosine of 225, 4 times sine of 225. Either way, what you get is negative 2.818, negative 2.818. Yeah. And now we have to deal with this force. And this is where this problem gets confusing. We use this angle of 45 degrees to get that row vector. But to come up with the direction of that force, that 45 degrees doesn't mean anything. All that matters is the direction perpendicular to that slot. So again, I'm gonna do it like this. I'm gonna draw my coordinate system. And we know that that slot, we're told that it makes an angle of 20 degrees with the vertical. Okay, so I'm going to draw a vector that's 20 degrees from the vertical. And now the force we want is 90 degrees from that. Okay, so this angle is 20. This is a right angle. And so now for this, my theta is, I'm going to go from the positive x-axis to this one that's 20 degrees from the vertical. So I'm going to go theta is equal to, this was counterclockwise, so positive 110. Then I'm going to go clockwise 90. And so I get a final answer of just 20 degrees. And so this, now that 4 doesn't matter at all, okay? The only thing that matters is we're trying to come up with a unit vector in that direction, and we're going to multiply it by the variable n. A unit vector in that direction is cosine and sine of 20 degrees. So this force is cosine of 20 degrees times n, sine of 20 degrees times n. Any questions about that? That's the trickiest part of this problem. And then you get an answer of 1.685 N. Anyone have your answers in front of you? Is that what you got for that?
1.69.
Okay, yeah. Yeah, I don't care where you round it off. In a computer program, you're going to be keeping a lot of digits, you know, the program is going to be keeping a lot of digits. Okay, and then the last one, the reason I did it last is because now we want the midpoint of these two, right? We want the row vector for the midpoint between those 2 points. This is a cute little thing. This works for the coordinates and it works for the row vectors too. If you want the row vector for the midpoint between these 2 points, just average the row vectors and that's the row vector of what you want. So
Minus 1.409.
yeah, let's see. So minus 1.414. Oh, this should have been 2.8. Oh no, that's gonna change my stupid cross product. 828. Oh, that's easy for me to switch though. I have it right here. Oh yeah, so it does go to so 1.691. Yeah. Okay, and so average those two and you get negative 1.414, negative 1.414. The weight force is 0, negative 8338.5. And the cross product is 11,790.6. And so now, maybe I'll stop there, but now you can solve that. And so your intuition and mine were the same at first. They were both wrong. What's happening is because all this can do is rotate around this pin, this thing wants to move perpendicular to a circular path. That circular path would let it go this way, which means that it's being pushed out by that slot.
So it's basically like resting on the slot.
Yeah, it's resting on the right
the
side
slot
of.
is putting a force
Yeah.
in the other direction.
Right. Yep. Exactly. Anybody have any questions about that one? Okay. Any other homework questions you want to see? Okay, so now let's get into 3D joints. And so before I do this, let's talk about the degrees of freedom. In 2 dimensions, imagine an object just out hovering in space. And imagine the ways that it can move. So it can move along one axis in translation. It can move in a perpendicular axis, along a perpendicular axis in translation. And then it can rotate about a third axis. So this is a rotation. And so those are 3 degrees of freedom. And in order to come up with the loads that a joint applies to the body, you think about which of those are eliminated. And by the way, think first, if any motion is restricted at all, think first about the translation that's restricted to choose the perpendicular axis. Okay, so like if you have like imagine a frictionless contact like this. Don't think about first what you want to choose as your X and Y axes. Think first about like, okay, it's definitely, a motion is definitely restricted from sinking into the surface. So that's going to be your first axis. Then choose, now that you have one axis, choose the perpendicular one after that. Okay, just intuitively to think about those. So the first axis here would be this. So when motions,
choose your axes, you just mean choose your unit vectors.
yeah, right. So choose your first axis as one where motion is restricted. Okay, so now let's think about what happens in 3D. Well, what do we expect to happen? We just had this question come up in a quiz. Oh, I have your quizzes, but they're in a different room.
One additional translation axis and two additional rotation axes?
Yep, so we have 3 degrees of freedom for 2D, but we go to 6 degrees of freedom for 3D. So let's think about how that works. So the body here's the body in 3D. And the translations are pretty easy to visualize. One is that way. There's a perpendicular one that way. And then another perpendicular one that way. Okay. The rotations, now notice, so in 2D, you can't rotate about this axis. That would be like this. Okay, tumbling like towards us. You can't do that though and stay and keep this body confined into the plane. Okay, so that axis of rotation doesn't exist. Okay, and you can't rotate this thing around that axis for the same reason. You know, you can't, if you try to rotate it like this side tries to come out of the plane and that's not allowed. That's why there's only one axis of rotation in 2D. Okay, but in 3D you can rotate about all those axes. So what you have is a rotation like that, a rotation like that, and a rotation like that. So there's 3 of these in translation. And 3 rotation. And in going through these joints, we're going to think about it the same way we did in 2D. Anytime a translational degree of freedom is eliminated, there's going to be a force that does that. And anytime a rotational degree of freedom is eliminated, there's going to be a couple that does that. Okay? So here's a list of 3D joints. And a couple of these are going to be a little tricky. Okay, so I'm going to go through it the same way I did in 2D. I'm going to talk about, like, I'm going to start with ones that introduce one variable into the equations and go all the way up through 6. So joint category 1. These are joints that apply a force in a known direction. And so these introduce one variable into Newton's laws. And there are two of these. The first one is a frictionless contact. Um, okay, I'm going to call this body 1 and the surface that it's in contact with body 2. And a free body diagram of body 1. So there's the body. And if the surface, if that's like an outline of the surface, then the force is going to be perpendicular to that. And you would represent this with a scalar variable, not with a vector variable. So just call this R or something. And the second one in this category would be a roller. So I'm going to try to draw this. Oops, I didn't give the title. So this is a roller. And this is like a ball, not a wheel. Okay, the reason this is a ball and not a wheel is that this can't have any preferred direction. So if you see a wheel drawn, the implication in a 3D problem, if you see a wheel drawn, what it's implying is that it can roll along the direction the wheel's pointing, but it can't slide. Okay, so that would have a preferred direction. This doesn't have a preferred direction. And so a free body diagram would look like, I don't want you to kill yourselves trying to make stuff look artistic, but I try to, when I'm doing these, to make it clear what I'm outlining, so that's why I'm doing that.
The amount of lines that I've erased and redrawn is just
Yeah,
much.
right.
I appreciate it. It's actually helping my drawing skills.
Uh-huh. I think it's surprising how many times doing a clear drawing can help you visualize a problem right, you know? But the basic idea is the same as a frictionless thing. So those two, you can think of them as meaning the same thing. One thing to notice about these is that R must be positive for both of these. Neither of these can pull on the surface, that means. Any questions about those? Oh, wait, what? It's plugged in. I want to appeal. Okay, so now joint category 2. So this applies force components in 2 directions. And because of that, this introduces 2 variables into Newton's laws. There's only one of these. And this one is a wheel with a preferred direction. So this is like the other type of roller. Notice that if you're doing a problem in 2D, well, let me draw this. So nope. Yeah, right. But how did that did not look right. That's better, I guess. Okay, so
I pulled it out of the bin at Menards.
yeah, exactly. This has a preferred direction. It can only move along this line. Notice that if you're doing a 2D problem, whether you see something like this or something like this is irrelevant because all it can do is move in the plane. But here, there's a difference. I'm going to call this body 1, body 2, and a free body diagram of body 1. There is a force that keeps it from sinking into the surface. I'll call that N. But then there's also a force that keeps it from sliding off of that line, that preferred direction. And both of these are perpendicular to the line, the preferred direction line. So this is perpendicular and this is perpendicular. Okay? And these two are perpendicular to each other. Any questions about that one? Okay, so now joint category 3. I think all the ones from now on just have single types of joints in them. Okay, so we know that joint category 3 has to introduce 3 variables into Newton's laws. It's going to be, a force with 3 unknown components just means a full force vector, a force vector where we don't know the direction. Can you think of what type of joint would apply?
Like a ball and
Yeah, exactly, a ball and socket joint. So this is a force vector with a fully unknown direction. So all translations are restricted. But there's still no restriction on rotations, or let's say all translations are eliminated. But it's free to rotate about any axis. And this introduces 3 variables into Newton's laws. So like you said, this is a ball and socket joint. Something like that. That's a pretty shallow socket there, but so call this member 1 and this member 2. Free body diagram of member 1 would look like this. You don't know any of those force components, and we could write this variable as the force on body 1 by body 2. And then if you were drawing a free body diagram of body 2, you draw all of those axes in the same directions, just in your coordinate system directions. And the force you would write as, well, you could write it as F on 2 by 1. But more importantly, that's equal to negative F12. So this is the one that you'd want to use in Newton's laws, because otherwise you're introducing unnecessary variables into the problem. Yeah.
Is this only for frictionless ball and socket? Right?
That's correct. Yeah. Right. So in statics, yeah, if you had a ball and socket with friction in every direction, in statics would just be a fixed joint. Any other questions about that one? What joints do we have here? Okay, here's a ball and socket joint. So thinking about this, just, yeah. So you can see if you try to translate, I'm going to say my x-axis is this way, and I'm going to think of the socket is fixed and just try to move the point of contact this way. You can't do it. You can't move it up or down. You can move it up if you pull hard enough, but and you can't translate that point out towards you or back towards me. But now let's think about the rotations, because this is kind of this is the new thing from 2D that you haven't had to do yet. Okay, so this is our x-axis. What does it look like for the top to rotate about the x-axis? That would be like this, and that's allowed. Okay. The y-axis is, so this is x. The y-axis, let's say, is out towards you. So right, exactly, that's going to be like that. And then the z-axis is up, and that's like spinning this thing like that. Okay, and all those are possible. Okay, now joint category 4. These next two are the trickiest to work with, and you just have to remember some stuff about them. So this is this applies two force components and two couple components. And this introduces 4 variables into Newton's laws. And the joint in this category is a pin joint without thrust. So darn it. Try this again. Okay, so here's the pin. Here's one of these two bodies. Here's a little length of the pin between the two bodies. And then here's the other body. And then I'm just exaggerating this pin, but so what thrust means is an axial force, a force along the axis of that pin. And so you can see from that picture that both of those are free to slide along that pin. So there's no force provided there. And I'll call this body 1 and this body 2. And a free body diagram of body 1. Okay, let's think about how these motions are restricted. So that pin keeps this thing from moving up and down, right? So there's a force that's this way on that pin, and it keeps it from moving out and back. So those are the two axes of force. But the axis that isn't restricted is along the pin. Okay, so those can be, as long as those two force directions are perpendicular to the pin, you can put them in any direction you want. Just put them in your coordinate axis directions. So I'll call this Rx and Ry. this would make it a little more clear. Okay. But there's no force along the axis. Are you with me on that? I'm going to move this label out of the way. Okay, and now what about the rotations? So what rotations does this allow? It definitely allows a rotation about that axis, right? But it doesn't allow a rotation this way. That thing can't tilt. Do you see that? And it doesn't allow you to spin from the top. Okay, so those axes are the same axes as the forces. So this is an x component of a couple and a y component of a couple. Yeah, sorry.
Is it necessary to combine them like that rather than, say, like drawing one like right inside the other one? This?
No, it's not necessary. I think people accept that no matter, like, as long as it's clear to you, people can deal with it. Yeah.
I'm just worried about fitting that to everybody.
I know. Well, okay. So here is the important thing about these. Usually, these aren't going to appear by themselves like this because, so I said that these things restrict these couples. This doesn't allow it to flop, side to side along that axis, and it also doesn't allow it to twist. But if I handed you this 3D printed thing and said, try to break this thing, those two moments are exactly what you would apply to try to break it, right? That's where this thing is weak. It's not very good at applying those couples. It'll do it if that's the only, it'll try to do it, but it's not very good at that. So most of the time, these won't be applied by themselves. They'll be applied in pairs along the same axis. And the reason you apply them in pairs along the same axis is that when you do that, the joint isn't responsible for providing those couples. The two partnered joints have the effect of providing those couples.
Are you saying kind of like on like an excavator bucket?
I'll show you what I mean here, just a second, but let me get this written. So don't include the couples when the joint is part of a pair of coaxial pins, sharing an axis. Okay, so this is a little hard to see, but it doesn't apply thrust because this can slide side to side. But now think of this joint as, think of this as a pair of pin joints without thrust. If it was a single one of these, it would still prevent you from tilting this pin this way and that way, and it would still prevent you from twisting this. But notice that with the two of these here together, they do that by just applying forces. Like now I can't make it rotate this way. and it's not done by either one of these two. It's not prevented by either one of these two keeping it from rotating. It's prevented by this one applying a force one way and this one applying a force the other way. And the same thing with me trying to twist it like this. I don't have to use this one to apply a couple. I can apply that couple by just applying, like the couple basically becomes the force going one direction on this one and one direction on the other one. Okay, and so if it's in a pair like this, you're much less likely to be able to break it by twisting about those axes. And so that's why you usually see it in pairs.
So if you did include a couple, they would just cancel each other out?
If you did include a couple, like if you put it,
give an about point.
if you're like, I want to be safe about this, so you just still did include those variables in there, you wouldn't be able to solve the problem.
Okay.
Because you're introducing two more variables and with no more equations. Okay, any questions about that? We'll finish up the last two next time, and then we'll do a bunch of problems.